Let me share my screen first. Yes. We're just talking about the memory allocation. So in memory allocation, we are usually talk about contiguous memory allocation. And here is two types. One is the fixed partitioning, another is the variable partitioning. When many talk about the contiguous memory allocation, we actually didn't talk about the non-contiguous memory allocations. So if you see the fixed partitioning, there is some problems like internal fragmentation problems, some major problems. In fixed partitioning, what we did, we actually at the beginning, the RAM is divided into some fixed partition, and OS and your operating system actually insert a process within this fixed partitioning. It has no extra flexibility to actually it's never, your OS can actually never go beyond these partitions, number of partitions in your memory. This is one of the drawbacks. Also, we saw that in fixed partitioning is suffered by the internal fragmentation problem. Also, then we talk about the variable partitioning. Variable partitioning is nothing but there is no at the beginning there is no actually a fixed partition, or there is no partitions. Whenever the process comes, it will allocate RAM will allocate the memory for a specific process, and actually it's insert the process as many as it can. It depends on the size of the RAM, but problem is there could be some external fragmentation problems. What is the external fragmentation? There could be even though there is space is available for a particular process, but it is not in a contiguous location. It is in different locations, so you cannot fit the process inside the memory. Yeah? It creates a problems called the external fragmentation problems. And then we actually saw some memory allocation algorithms, how actually we allocate the memory. Actually, what's kind of memory allocation algorithms OS can use, your operating system can use to fit a process inside the RAM. There are 4 types of memory allocation algorithms we talk about. One is fast fit, next fit, best fit, and worst fit. Also, we saw some examples to figure out which algorithm is better, and then we actually conclude that there is no we cannot decide that which one is better than others. It depends on which order your process comes into the RAM, also the holes that is created inside in your RAMs. This is 2 parameters. It depends on these 2 parameters, but we cannot say that okay, fast fit is better than fast fit is the best algorithm. We cannot decide this way, but yeah, it's completely depends on your process process sequence as well as the hole that created inside your memory or RAM. So these are the things we actually learned in our last class, and today let's talk about some variable memory partitioning as external fragmentation problem. These kind of stuff we have explored, and then we'll go for this non-contiguous memory allocations. Okay, so before I start, let me stop and let me open my whiteboard from my iPad. So let me share my screen from here. Okay. So if you look at the we already know that if you use the variable partitioning, there could be some hole inside. If this is your memory or RAM, when your OS actually OS actually insert some processes inside the RAM, this is occupied, this is whole, this is also occupied. Let's say this is whole, and this is also whole. Let's say this is 5 MB. This is, let's say, another 5 MB is available, and this is another let's say 2 MB in here. Whole is here. So now 12 MB. If your process is if now you open another program or software, whatever it is a kind of one kind of processor. Now you open another new process. Let's say its size is 15 MB new processor. 15 MB new process is created in here. So what your OS does, OS try to actually search from your memory, from its current structures, and then it says, okay, this is occupied, this is occupied. Here is 5 and 2 is available, but 15 is available in here. Let's say this process size is 12 for simplicity. Let's say this is for our understanding. This is for 12 MB. 12 MB process. You actually OS search your memory, search from starting. If it is fast bit, it search from starting, and it's never find a suitable hole to feed it this 12 MB in a contiguous locations. But still here is 12 MB is available, but it is in different location, not in contiguous. Let's say this is 0, 1, 2, 3, 4, 5 space, 5 memory addresses, but it is not in contiguous. Whole is in one, a memory address is at 1, and another is at 3, another is at 5. We cannot feed this, even though this 12 MB free space is available in your RAM, inside your RAM, but you cannot feed it because you are now using the contiguous memory allocations. Contiguous memory allocation. In this type, all 12 MB should be in a contiguous location. So how you can resolve this issue? How we can actually solve these problems? There is two things we can consider. One is called the compactations. One is called compactions. And another I will discuss later. How compaction works. What it said, that after a certain period of time, after a time interval, what it will do, actually compaction algorithm, how it works. After a certain time interval, let's say every 1 minute. Every 1 minute is very long time for CPU, and also in your process management CPU. Let's say every 1 minute, what you do, what compaction will do? Compaction will do all makes the all holes together and all process together. What does it means? Every 1 minute, later, there will be what you want to do. Every 1 minute, interval, CPU will execute a let's say program that will makes all process together. Oh, sorry, let's say not in from. We can make it in here. What it does, CPU will copy this process in here, and this is now in hold, and also this process, and this process should be copied in here. So what it is in here. So now this process is actually moved to up here and here. So now what it was, it is 5 MB. This is also 5 MB here over there. So now you can see that this all process right now in together, and all holes are in together right now. All holes are together. So now, sorry, this is now a big hole in here, and this is all processing together. So this is how you can solve your internal fragmentation problems. So every certain time interval, here our assumption is every 1 minute's time interval, or every 5 minutes time interval, or every 30-second time intervals. What CPU will do? CPU will copy this all process together and all make there's the all whole together contiguous location and all process in a contiguous locations. And now you see there is 15 MB is available, so you can fit your process in here, new process in here. So so this is how you can solve your internal fragmentation problems. But here is a problem. There is one major problem is that you know that every time you have to every 1 minute or 2 minutes, 5 minutes, whatever the time interval, you have to copy and paste your one process to another location from here to here, also here to here, here to here. It could be you have to copy and paste. This copy and paste takes time. Always copy and paste process, it takes time. This is one. So it will be time consuming first of all. Also, if you consider every 1 minute's time interval, you want to do this process. You want to do this process means you want to do actually copy all process together and all make all holes together. So every 1 minute's time interval, what CPU requires to do? CPU wants to call one function from your operating systems to make the copy paste things, to make this whole together and also process together. If you consider this every 5 minutes or every 5 minutes or 1 minute, whatever it is, CPU requires to call a subroutine from or function from your OS. There could be some special function. What it will do, it will make all process together and all holes, gets the all whole together. From here, what you can actually understood that is, so whatever you are doing currently, let's say you are right now, you are just in your computer, you are doing some typing. You are typing currently. You are typing a MS Word document. Also, you are hearing some music as well. So every 5 minutes interval, CPU requires to CPU actually stop your current process, and then it will actually start again and request to execute another actually internal process to make it copy and paste. So your process will be the slow execution. Also, every time it requires to execute as well as for the copy paste things, copy and pasting these items all together and whole together. So it takes it is another actually disadvantages for this compaction problems. So always it requires to do some additional works. CPU request for this request the WAS to operating system to do this copy and pasting. Right now, every 1 minute it will execute a process that will do these things. So it is another disadvantage for the compaction problems. Any questions? Okay. Okay. So, and let's see what could be the another things. Let's say you have a process in here, also in here. You have a two different holes. Here is 5 MB. Let's see, here is also 5 MB. 5 MB. And your OS, your operating system request for you are currently opening one process size is 10 MB from your DEX, and your OS trying to allocate it in here, but it is not in a contiguous location. But one thing it can do, it can divide it. If you divide your process, if you actually store your process to different location, if it is not in contiguous locations, it is fine. You can store your process in here, or 5 MB in here, 5 MB in here. Huh? So what does it mean? It is not in a contiguous location. Huh? It is in a non-contiguous location. So if you allocate, if you actually divide it, if you can divide your uh, process and allocate in two different locations, you can also solve the external fragmentation problems. Also, you can fit many process inside your memory or RAM. So in that case, you have to use the it is called non-contiguous memory allocation. Huh? It is not in a contiguous location. One start from here, one party is start from here, another party is start from this location. So it is not in non-contiguous allocation. Sorry, it is not a contiguous allocation. This is non-contiguous memory allocations. So one of the algorithm is called the paging. We'll explore it is in our next in next. So this is a basic concept of paging. Paging. Let me, before I explain the paging, let me explore some two or more other things. So paging and compaction can solve the external fragmentation problems, but compaction there are some disadvantages. But most of the memory allocation currently are using not all in our recent computers, we use the non-contiguous memory allocations. So before we start the non-contiguous memory allocation, let's see in one more item. It's called binary addressing. How you can address it? How actually binary addressing is works? Let me explore that thing. Then I will explain another contiguous and non-contiguous contiguous allocation, how exactly works. And next we'll go for the paging. So currently, actually, I would like to talk about the binary addressing, how binary addressing works. Let me change the color bits. Sorry. Wait. Okay. Now, binary. Binary addressing. This is kind of basic of paging techniques. That's why you need to know about this binary addressing, so how it works. So before I explain the binary addressing, let me actually give you one example for real from our real life. Give you one real life examples. Let's say you have in a city. Let's say one arbitrary city. There is four road R1. Sorry, let's say start from R0. R0 is good because R0 is fine because computer is start from 0. So let's say city has a 4 road R2 and R3. And each road has, let's say, 2 park, P1, P0, P1. There is also P0, P1. There is also P0, P1. There is also P0, P1. There is two park for each road. P0, P1. So this is P1. P1. And each park, it has, let's say, 2 garden. It is G1 means that sorry, G0 is to explain Let me change the color also. Here is okay. G0, G1. That is also 2. Score. Let me little bit here. Here is also G0. Okay, this is I think another is if you don't put this P0, it will go for numbering system. This will be okay. This is P0, P1. Sorry, let me change the color again. This is P0, P1. This is P2, P3, P4, P5, P6, P7. That is G0, G1, G2, G3. There is also G4 and G5. That is G6. G7. That we can say that is also 2. G8. Then we are now out of space. So G8, G9. Okay, let's say so how many will be? G15. That will be the G15. Total 16 garden will be there. If you think about this, yeah. So this is binary representation. A particular thing is root. It has only two children, two cells. So it is a binary representation of any. That's any. This is for the road system. Road and is road. It contains two part. Is P0 P1 also. Its part. It has also two garden. It's called G0 G9. So here is total four roads we consider. Here is total how many it will be. Here it will be the 8 part because each road contains the total each road contains 2 park. So total 4 contains total 8 parks. And then here is garden, total garden. So total it will be the total 16 garden will be there. 16 gardens. 16 gardens will be there. So how do you represent the total 16 garden? I want to actually look at each garden uniquely. So for this total 16 garden, to addressing total 16 garden, how many bits is required? We need 2 to the power m items, actually 2 to the power m items to represent this 2 to the power m garden or m items. We need how many bits? M bits. We need m bits. So here is total 16 garden of 16 garden or 16 items. So how many we need? 2 to the power 4 equals 16. So we need total 4 bits to represent the each garden uniquely. Uniquely means that this is 0, this is 0, 0, 0, 0. This is 1, garden number 1, 0, 0, 0, 1. This is 0, 0, 0, 0, 0, 1, 0. This is that one is garden number 3. This is 0, 0, 1, 1. And here we'll find the 1, 1, 1, 1. If you look at this way, total 4 bits is required to uniquely identify each garden. So it is start from 0, 1, 1, 2, 3, 4, and then 16. This is binary representation. So from here you can identify each garden this way. That this is 0 number garden. This is 1 number garden, 2, 3, 4, and 16. So on. Another way you can represent this garden from your start from your road and also park and garden from this bit. How to do this? From for the four roads, to represent these four roads in a binary or four items in a binary, how many bits is required? We need 2 bits. So for four numbers, or there is 4 items. So 2 to the power 2 equal 4. So here is there is 4 roads. To represent this, we need only 2 bits in here. So how to represent it binary for road 1? It is 0 0 0 1 and then 1 0 1 1. So 2 bit is enough. 2 bit is enough to represent this. This is road uniquely. Represent is node uniquely for 2 bits. Also, and here is road contains two park. To represent this park, how many bits? Two park. How many bits is required? Only 1 bit. Either 0 0 park 0 or park 1. There is park 0 or 1. From here, you can see also, and then each road also, each park also contain how many garden is 2. Here is also 0. There is total 2 park. 2 park contain total 4 garden. 4 garden. It is associated with the single road. 2 park contain 4 garden. If you consider this way, so this 4 garden needs require another 2 bits to represent the total 4, like this road. So from this 4 bits, let's say one particular garden, this garden, how we can interpret it in different way. Let's see. Let's say this first 2 bits. 2 bits is considered as a road number. This is road number, and also 1 bit requires the park number. 3rd bit is for this park number, and then how many bits is left? How many bits is also last 1 bits also represent the garden number, because it's particular park there is 2 gardens, so it can represent also 0 and 1. And last 1 bit you may represent the this is for park number. Let's say park number, and last bit is for this garden number. This is for G garden number, 1 bit. So if I interpret the 0 0 1 0 0 0, so 2 bits is road number, and 1 is for this park number, 3rd bit, and last bit is for garden number. So from here you can start from this 0 0 means this road 0, road number 0, and then park number 1 means that one park number 1. This is 0 number park, this is 1 number park, so it's go to park number 1, and then garden number 0. Garden number 0 means that one. This is 0 garden, this is 1 garden for park 1, this is 0, means that you will get this number. So you can either interpret 0 0 0 uniquely by using 16 number, or you can interpret this number by using some segmentation. From start from road, let's say you want to go the 0 0 1 garden from let's say 1 from this garden number, using garden number 1. What is let's say you want to go to this garden number 0. Here is what is the number? All 0 4 0. So first 2 bits is for road number, and this bit is for this park number, and this bit is for garden number. From here you can start. This is 0 0 for this road 0, and then garden is 0, sorry, park is 0, this 0, and garden 0, and this 0. So either you can identify 0 0 0 4 0, or you can actually go through from this road number, park number, and garden number by segmentation. So 2 way you can interpret any binary addressing. Any question? Okay, so I actually explained this thing for one reason. So let me explain clearly. So if you, let's say, in a particular process, in a certain time, your computer has total 4 process. Let's say P1, sorry, P0, P1, P2, and P3. Total, total 4 process. And each process contains, you know, that total, let's say total 4 bytes or 4 word. You know the word, and you already know about the what is the word, and as well as the what is the byte. Word contains minimum word contains 2 bytes, and 2 bytes also, if byte is the 8 and byte is one byte is 8 bits, huh? So one word is 16 bits, also double word is 32 bits, kind of like this, huh? So this process, let's say is this process P0 contains 4 bytes or 4 words. Let's say 4 words, it contains 4 words, 1 2 3 4, huh? 0 1 2 3, this 3 these 3 words, huh? These 3 words, this process contains 3 words, or yeah, 3 words. P0 process contains 3 words. Also here also it can also make process 0 1 2 3 3 words as well. So how actually CPU can uh, CPU can execute the word number 3, word number 3. Let's say it is byte word addressable memory. There's two kind of addressing things. One is the byte addressing, another is the word addressing. What is the byte addressing? You in your memory, each byte has its own unique address. Each byte has its own unique address. It is similar to the, if you memory is word addressing, means that each words contains a each word contains a specific address or unique address. So let's say this, forget about the byte word addressing. This is, let's say this is for byte addressing. Each byte contains a unique address. This is yeah, each byte contains a unique address. So how a CPU can execute this byte P3 uh, P3 bytes? How it can do? That is total. That is total 4 process. Total 4 process, and each process contains total 4 bytes. So 4 into 4, total 16 bytes. Here is total size is how many bytes? 16 bytes. And each byte has its unique address. Unique address. So how actually CPU can actually execute this execute, let's say, any particular bytes uh, data from any particular bytes. How CPU can execute? Let's see it. So one thing is that I mentioned earlier, that you can uniquely you can give it 0 0 0 and all 4 all 4 byte in 40 in here. This is 1 0 0 0 1, and this is 0 0 0 2 for 0 0 1 0 and 0 0 1 1 0. This is 4 5 6 7. This is also 8 9. This is also, this is 4 byte, 4 number byte. This is 5. This is 6. This is 7, and so on. This is 8 9 10. This is 11 12 13 14 14. This is 15 bytes total. Total 15 by 15 means 16 byte total. Total 16 byte. So how CPU can either execute take its specific byte, but it doesn't work this way. It works the example that actually we have seen earlier. So from this 16 byte, how CPU will do? CPU will for this four process, 16 bytes requires by addressing this 16 byte, that is total 16 number, 16 address, 16 address requires to addressing 16 bytes. If it is byte addressable memory, we consider it is a byte addressable memory, and there is total 16 bytes. So it takes total 4 bits to address this all 16 bytes. So let's see, I want to execute this byte number 3. So what is the address for, if we consider binary addressing, what is the address for? It would be the 0011, number 3, 0011. And for a process, here is total 4 process. 4 process uniquely identified for 4 process. How many bits is required? That is required 2 bits for addressing total for 4 process. So here is 00 process for 0. This is 01. This is 10. This is 11. Process number 3. Total 3 process. Sorry, this is 11. This is total 3 process. So 2 bits I will consider for first 2 bits consider for this process number, and last 2 bit will consider for this byte number. This is for byte. This is for byte number, process number, and last 2 bit is for byte number, allocation for this byte number. So how it works? So if CPU wants to execute the process 0, first 2 bits means this is process 0, and then last 2 bits means the byte number. So this is 00. Each process contains total 4 bytes. So 4 bytes requires another 2 bits. This is 00, 01, 10, 11. So by using this number, or by using this address, which location we can execute? First is 00 means process 0, and 11 means this byte, exactly this byte, this number, this byte. If it is, let's say if it is 1011, if CPU request for this address, execute for this address, what would be the where actually it will which part it will executes? It is 10 means the process number 2, and 11 means this byte number 3, this byte. Also, if it is 1110 means this process number 3, 2 bytes represent this, first 2 bytes represent process 3, and last 2 bit represent this byte number 2. This is byte number 2. Sorry, yeah. So this one. This is 01, this is 2, byte number 2. This is 2. So this number. So if it is 1111 all 1, so which one it will execute? This is process number, it will hit the process number 3, and then byte number 3 means this 16th byte, 16 byte. So this is how actually CPU if it generates the address, this is how actually it execute is byte in your process. Any question? This is kind of some basic of your paging. When you explore the paging, then it will be the more clear. Okay. Let's see another items in our compaction and our in our contiguous memory allocations. In our contiguous memory allocation, how actually CPU performs, asks for a data. Now actually what we saw previously, we just saw that CPU just asks for this data, and OS just OS manage this process and send the data to the CPU or CPU register to execute the process. Yeah, execute the process. This is how it works. let's see some closer look how CPU actually works in for a contiguous location. Then we'll go jump into the non-contiguous or paging techniques. Okay, let's see. Let's see. This is taken I draw. This is your RAM, and CPU is asking you just open some processes and your OS actually fit some processes, some location inside your RAM. This is for process P1. This is for process P1. Also, let me addressing some part in here. Let's say this is 0. I'm just addressing as a decimal number. This is 100. Here is, let's say, this is some whole, and here it is start from 200 again. Here is also one process P1, and here is also one whole. Here is also, let's say, one process in here. There's also one whole in here. So how is a process look like? Process P1 is here. You have two process. Here is, let's say, here is two process P2. Here is process P3. How process addressing process? Every process has its own logical address. Logical address is always start from 0. This is 0, 1, 2. This is what is the logical address mean? The is line or is instruction of your processor. Is instruction of your process. Process is has its own logical address. This is 0, 1, 2. Also, this is not actually 100. You'll be the confusion confused. So let's say this is also this is 0. Also, this is 1 physical address. Also, this is also 2 as well. 2 as well. And then here is also, let's say, here is process logical address is 0, 1, 2, 3. Here is, this is for physical address is start from 200. Here is 201. Here is 202. Here is 203. There is also another process that this is start from 500. Here your process also some logical instruction 0, 1, 2, 0, 1, 2, 3. Let's say 4. This is for 500. This is for 501. This is 502, 503, 504. 504. So how actually CPU execute this contiguous memory allocation? So how CPU execute when actually asks for this process P1, P2, and P3? CPU, let's say CPU currently CPU execute the process P2. CPU actually knows only it would likes to execute the process P2. Its zeroth first instruction or 0 number instruction, then 2, 1, then 2, then 3. Also for P3, CPU execute the process 0, number line instruction 0, 2, 0, 1, 2, 3. This way CPU will execute. But how CPU actually currently know where is process P1 is start from this 0th physical address, but others two process actually started from 200. Start this 200. Another process another is located starting location at 500 address. So how CPU actually send instruction for execute process P2 as well as the process P3 and P1. What CPU needs to know? CPU needs to know the base address or starting address of a particular process. When you create a new process, in if you consider the variable allocations, memory allocations, when this is, let's say this is 5 MB. 5 MB is free space. So you create a new process 5 MB. Here is, let's say here is the 2 MB. You create a new process for 5 MB. 5 MB. Then your OS actually search the location for this 5 MB and it will find in here and it will fit this 5 MB process in here. Let's say this is 0, 1, 2 number instruction for your process. This is, let's say this is process P4. Also it is at 203 or 200. This is 204. This is 205. This is 206. So how CPU actually and CPU generates start from the 0, 1 to only logical address, but how CPU will get this physical address? Otherwise, it cannot execute a process. So what actually OS does in that case, when you create a process, OS will manage, your operating system will manage a process table. Huh? It is called the process table. When you create a new process, in what is a table? Table is nothing but some rows or entries. Huh? There will be some entries. Huh? Process will, when you create a new process, CPU, your operating system will maintain a process table. In every process table, it will maintain its, let's say here is, we currently we have total, how many process? 1, 2, 3, 4 process. P1, P2, P3, and P4. We have total four processes. Huh? So how CPU will do? CPU will manage the maintain this process table. Process table, PT. Let's say in short, let's say PT process table. What process table will do? It will actually store the base address or starting physical address of your newly created process. Whenever you create a new process, it will actually insert an entry in the process table, and it will give the process name as well as its starting physical address. Process 1 starting location at physical address location is 0, and process P2 starting location is 200. Physical address. Physical address means the address space in your RAM or memory, and logical address is address space in your processor. All physical address address space also starting from 0, or is also your process your logical address space or your process address space is also starting from 0. Huh? So there is when you create a process, it is 0, 1, 2. This way, it's just addressing. If you create the 2 or 3, everything will be starting from the 0, 1, 2, 3, like this way. But what would be its physical location for a specific process? It will maintain in a starting address maintained in a process table. So, and another process is P3. P3 started at 500, and you create a new process. It's P4. It started, let's say, 203. It says manage a process table. So what it does when CPU is executing a process, CPU, this is CPU, and it has, also you know that in CPU it has some different types of register, and one type of register is called the base address register. Huh? One type of register is called base address register. So what CPU will do? CPU will when CPU execute a process, it will search in the page table. Let's say CPU will execute the process P3. CPU currently will go for this. Currently is now actually working on the process P3. So what it will do? It will search in the page table. In process table. Your process table. It will keep search in process table and figure out that what is the address, starting address, physical location, starting physical address location of your process P3. It is 500. So 500 actually loaded in here in your base address register, starting location of the process P3. So it's stored in here, and then CPU generates the number for 0, 1, 2, 3 kind of logical address for executing the process P3. That's how it works. It will generate then it will ask for the first instruction, means the 0 number instruction for the process P3. It just what it will do, it will add the base register value plus 0. Oh, one more thing I forgot to, you may think about, okay, CPU doesn't know. Also, you know that space table is kind of, this is a table, it also needs a memory. It will be in some memory. This is, let's say, in here, this is in here. This is the space table should be inside your memory as well. Huh? As well, everything should be inside in your memory as well. So space table should be inside your memory. So you can ask me that how actually CPU gets this space table, process table location. So I just repeat, this is process table, not space table. This is process table. How CPU gets the process table locations? So the answer is process table is always located in a fixed location. It is inside the OS, where at the inside the OS, it is always located in a fixed location. So whenever it executes, your CPU actually searches in the particular or fixed location for this process table and find the process number and load the base address and load the starting address inside the base register. This is how it works. And then it will ask for the 0 number instruction or first instruction. Then what it will does, it will just add the number 0, whatever the instruction it wants to execute, it just add within the base address, within the base register address. Let's say it's now currently it will execute the first instruction or 0 number instruction. So what it will do, CPU will generate the 0 and add it to the base register value, and this is 500. So it will execute this instruction for process P3. And next time it will just increment one value. It will be the 501. And now from here, what you can actually observe, this is physical address location. This is how a CPU actually convert its logical address value to the physical address. It is easy. Logically 0, 1, 2, 3. It is consecutive. It is a contiguous location. So it is 0, 1, 2, 3, 4, like this way. And then it just add 0, 1, 2, 3, 4. It just add within the base register value. The value that is loaded inside the base register. It will get the particular instruction. So 501 means 501 for this physical address. So from here it will execute the next instruction. Then again 502, and it will execute the next instruction. And this is how actually CPU perform its execution process for a particular process in a different memory location. But it is for contiguous memory location. It is for contiguous memory location. It is very easy. It just add the base register value and just some addition perform some additional operations. Just add some value 0, 1, 2, 3, 4, 5 and execute the instruction sequentially. But if you consider the contiguous memory location, memory location, let's say some part is process P1 is start from 0, and here is some part is another process, and here is, let's say, that is also some another process. Here is also this part is start from, let's say, 100, and here is also process, some part of this process P1. This is process P1. This is for another process P1. So how CPU will work in that case? Also CPU, let's say CPU try to execute the process P1, but it is in non-contiguous location, in different location. So how CPU will perform this execution process? It can execute, let's say this is 0 number address. So it's in base address is load currently now 0. It's load the base address value as 0. As 0 in here, and it add 0 for first instruction, then second, add another one for this second, and then another one for this third instruction 3. But if now it requires to add another let's say fourth instruction, try to execute, but fourth instruction is for this another process. It is fourth instruction is located at, let's say, 100th location. So from here, in simple addition, it is not possible to manage to execution process. In contiguous location, you can simply add some value. CPU just simply add some value or increment one value, and it can execute the instruction. But in non-contiguous process, CPU cannot perform the execution process just adding a new value, just adding or incrementing a current value. It is not possible for contiguous location. You see, it is not possible. So somehow CPU needs to manage some other technique. This is called the paging. Again, I said this is actually paging. What CPU does, instead of CPU maintain the process table, CPU will manage. It is called the page table. CPU needs to manage operating system. What CPU can your operating system will manage a page table for every process for in case of non-contiguous memory allocation. Okay, so do you have any question or comments regarding the contiguous execution process of contiguous? And you see that if it is non-contiguous allocation, you cannot actually access the process sequentially. Yeah? It is in two different locations. It is always in here is only 2 different. It can be 100 different locations. So for simply addition, it doesn't work. So you need some special technique to actually process to execute process from different location. You need your operating system will maintain a page table for each process or every process. Whenever you create a new process, open a new process, it will create a new page table. It is not a single page table for all process. It will create a new page table for every process for execution purposes. Okay. So do you have any question or comments? If no, today this page table process is it is little bit lengthy. So let's we'll talk about our process table from our next class. Okay, before we go, do you have any question or comment? You can ask me or you can email me. Also, I uploaded all of our recording in our module folders. You can check from there. Okay, thank you everybody. Have a good evening. See you next class.